And so now we have Fubini's theorem, which I mentioned in the last clip, allows us to change the order in which a double integral is computed. And so it's actually, I know it in the most modern incarnation as the theorem of Fubini-Tonelli. So Tonelli came along afterward and sort of gave it some technical improvements, more suited to a graduate class. But so the basic statement is that if f is continuous on a rectangle R, then the double integral of f with respect to the area can be written with the y integral first on the inside or the x integral first on the inside, and it doesn't matter which. I don't really know anything about Tonelli. I can tell you that Fubini was actually a Jewish Italian mathematician, and during World War II, when Mussolini came to power and the fascists adopted the anti-Jewish policies of the Nazis, he fled to America and got a position at Princeton. He was part of the sort of World War II brain drain of people fleeing. Okay, so let's see. So that's the theorem. So there's another handy trick, and this isn't actually part of the Fubini theorem, but it quite often happens that the integrand is a function of x alone multiplied by a function y alone. So if it factors, if you can split it like this and you're over a rectangle, and that's important because we're talking about rectangles now, but later on we're going to look at integrals over more general regions. So it has to be an integrand that factors, and when you're over a rectangle, then if you look at the integral, the double integral from a to b, c to d of f of xy dy dx, like this, then let's see, so if we put in this formula that we have for the integrand, so g of x times h of y dy dx, now let's see. When we are integrating with respect to y, x is a constant, yeah? So any expression in terms of x is going to be constant with respect to y, right? It doesn't vary as y varies if there are no y's in it to vary, yeah? So that actually means that we can use our rule about integrals that say, hey, if you've got a constant, you can pull it out in front of the integral sign. So let's do that. So then this becomes a to b g of x times the integral from c to d h of y dy dx. Okay, so we've pulled that g out of that inner integral, and then I'm totally going to pull a fast one on you here. Look what happens. This inner expression, so it starts off on the inside as a function of y, but then we integrate it with respect to y, and we evaluate it across the endpoints of this integral. So by the time we're done, this entire blue box here is actually just going to be a number. And since it's a number, it's constant with respect to x. There's no x's in there to vary, so as x varies, it doesn't change. Well, so we can do it again, and we can pull that constant out of the integral. So then it becomes a b g of x dx times the integral c to d h of y dy. And so it ends up just being a product of two separately evaluated single variable integrals. So this is a very handy trick. I'll give you a couple quick examples. So if we take f to be x squared y on the rectangle 0, 3 cross 1, 2. Then the integral from 0 to 3, 1 to 2, x squared y dy dx. So let's see. So first thing to do is we pull this thing that's constant with respect to y outside of the y integral, and we write it as 0, 3 x squared 1, 2, sorry, integral from 1 to 2 y dy dx. And then we integrate, we do this integral right here. So that one here, you know what, I'm going to do it like this just to show you. A moment ago I told you that this thing in the blue box is a constant, and maybe that sounded fishy. Let me just work it out on the side here and show you what I mean. So 1 to 2 y dy. So we integrate this and we get y squared over 2, and then we evaluate it from 1 to 2, and we have 4 minus 1 over 2, which is 3 halves. So the guy in the blue box is just the number 3 halves. So this is 0 to 3 x squared dx times the integral from 1 to 2 y dy, which is 3 halves by our calculation from right up above. And at any point we can also go ahead and do the x integral, and we see that that's x cubed over 3, 0 to 3, and so that's what, that's 927 over 3, so 27 minus 0 over 3 times 3 halves, or 27 over 2. Okay, so there's our answer. So just the point of this was to show you that on the one hand it can be rewritten as just a product of these two integrals, and then also to justify why it works. Alright, so there's one example, and now hopefully that you believe me, I'll do one more quick example to show you that this works on infinite rectangles. So, oops. So the first quadrant actually can be written as a rectangle. It's just an infinite one. So it looks like this. And so now the trick is that I can split the integrand into e to the minus x times e to the minus y. Oh, sorry, that should not be a comma. That should be a plus. That's added together. So we notice that this guy here is e to the minus x times e to the minus y. And now we have something that looks like a function of x alone times a function of y alone. So we can split this and then notice that the y and the x, those are just dummy variables. Those could be anything. So in particular, I could put either of them equal to t. And then I just have to work out what that integral is. And so let's see, so that becomes minus e to the minus t from 0 to infinity. And let's see, so we have 0 minus negative 1. And then, so that's going to be 1. squared is 1.